Hello, everyone. So I'm back. It's work from home time at Materialize now, and we are going to try and talk through an example that I've got in front of me. This is something that feeds into Materialize, and I'll explain how. But it's actually, I think, a relatively small problem that we can constrain in differential data flow itself. And I'll set up the context and try to talk through what's going on there. So in differential data flow, I'm going to draw some pictures, see if I can do that. Also see if this is a good way to communicate information. What a great question. So in differential data flow, we have these streams of information that move through the system. They flow through various different operators like map and on to things like maybe a join and lots of interesting complicated operators that build up a data flow. The information that moves along these things, though, is fairly nicely structured, or it's important that it has a certain structure for differential data flow to work well. And in particular, that stuff always happens to look like streams of triples that have the structure data, time, diff. Where the types of these things are, let's say data, can be anything you want. Let's just say it's a string. So hello. Time is complicated, but let's just say it's integers for the moment. It's a thing that is going to advance as the computation advances. Let's just say 37 for the moment. And the diff, again, the easy case is it's a signed integer, so it's like, let's say +1 or -1. So maybe +1. And what this is saying is that at time 37, the record hello was added to the collection. So the +1 says the number of times hellos in the collection increased by 1, and probably it was 0 at first, and now it's one larger than it used to be. And this is the language of updates throughout the system. One nice thing that goes on is that maybe in the future, hello goes away, so maybe on 42, we get a -1. This tells us that maybe this was the only copy of hello. And so now at time 42, the count goes back down to 0, and the string doesn't exist in the collection anymore. But it's nice and explicit about what the change has occurred, and that's very helpful when we write our operators. It makes it a lot easier for us to, fairly quickly implement things like map, filter. A lot of operators work out pretty well because of this representation. Unfortunately, not everyone uses this representation. We're going to talk through a few other representations that people use. That can make our lives difficult if we don't correctly adapt to what they give to us. Let me give you an example, and you can sort of see where some of the trouble is. So let's imagine we're getting a different input here. One example is Postgres. By default, if you look at its change data capture output, it will tell you about new records with some nice primary key structure. So key, val, yes. At some time, I don't know, we'll still say time. And when it tells you about one of these records, there's sort of this implied +1 out there, saying like, well, key and val just showed up at some time, hooray. And what it doesn't tell you about is, let's see if I can successfully make some more space here. What it doesn't tell you about is in a deletion, for example. So when a deletion happens, it might just say key, question mark, at some other time prime, let's say, with an implied -1. So when there is some primary key structure on the data, it just says, I don't know, but like key, 397, yeah, it's gone. You figure out what the data is, I don't care. And presumably it does this because Postgres' life is a little bit easier if it doesn't have to go and look up the data that was deleted. Well, that means that we have to figure out what that value was. Another example is like a lot of IoT style streams come in with measurements. They might also have a key and some reading. We could call it just a val though, at a time. And the implied sort of semantics here are insertion or update semantics. So this has a +1. The first time we see something like this, but the next time we get a reading, let's say it's the same key and a different value, val prime, at some other time. What we're supposed to interpret this as is a +1 here, but also the same key, the old value at the current time -1. So we're supposed to retract the previous reading. We don't, our collection isn't supposed to have two readings for the same key. It's just supposed to replace the previous one, which corresponds to a subtraction of the previous one. Now, this isn't just busy work that we're doing here. Like, there's good reason to turn things into differential data flows. Framing, for example, let's imagine that the very first operator we have is not a map, but is a filter that looks at the reading and says, is this an anomalous reading? And perhaps in the IoT setting, we can the first value we receive, yeah, it's anomalous. So we can produce, our filter can say exclamation marks. That's scary. Now, some time passes, and we see key and val prime, and maybe val prime is not anomalous, it's not above some threshold. What do we do? If that was the only thing we saw, if we didn't see the data below, if this were not available to us, well, we got to go do all this work again of figuring out what was the previous value and all that sort of junk, because we don't really know if should we retract the alert? Are we transitioning from a alerting state to a non-alerting state? Do we have to just do you have to yell down the pipe not alert for everything that remains not alerting? It just seems like a big pain in the butt. So someone has to actually go and figure this stuff out if you want your operators to actually shut up when there are no changes, and we do. So what we're trying to put together is an operator, essentially like an ingestion operator that takes in data of some type. And what I'm going to do actually is make it be of type key, and then an option of a value at a time, with no pluses or minuses or anything like that. And the interpretation here is that this is a primary key. So as the data move through, the key identifies what's supposed to be one single value hanging around. When we get a value for the first time, if the key doesn't exist, we want to install the value. So the three cases, we can write them out. So if key does not exist, we want to turn this thing into key val t +1. If the key, and hopefully in that case, the optional value is set to something. I have no idea what should happen if we tried to supply a non-value for a non-present key. Let's worry about that later. Maybe it should be an error. Maybe we should just behave ourselves and not worry. If the key does exist, then we want to produce. There are essentially two cases here. If the optional value is present, we do one thing. If it's absent, we do the other thing. But in each case, we do k comma v old t -1. So we retract the previous value no matter what. And let's just say if the val is none, we just retract the previous value. And if the key does exist and the val is sum, let's say sum of v, then we're going to do both of those things. We're going to retract the previous value, v old, and we are going to produce the new value. I didn't subscript it with v new, but you can imagine that was the intent. So this is going to be the intended behavior of this operator that we're about to write here. It is going to take these statements that come in. If the key is not yet present, we're going to actually just produce whatever data is there. Maybe if this optional value is a none, we just do nothing. Like that seems like a sane thing. That's negotiable. If the key does exist and the value is none, we retract the existing value. That's like a delete statement, basically, where we just have the key. And if the key does exist and the value is set, we're going to treat this as an overwrite. We're supposed to retract the previous value and supply the new value as output. All right, now why is this hard? So this is hard because in some sense, we kind of need to keep a copy of the data around. Like we need to keep informally something indexed by key, recording the current state of the associated value. And that's fine. Like we know how to do that in something like differential. We're certainly going to use tech that does that. It's a bit annoying, right? Because we weren't necessarily hoping to do all that much work just to ingest some other people's data, especially if upstream people actually had all this stuff indexed lying around. So like in Postgres, that might be the case. You can change your Postgres configuration. In the IoT case, like it's less likely that you're going to be able to convince sensors to remember the previous value that they transmitted and to transmit the retraction. If nothing else, that's annoying for them. You probably can't trust them anyhow. It's more data to communicate and stuff like that. So we're going to write something. And we're going to do it, I think, in a way that has relatively small incremental cost. We're going to try and make it not too expensive, at least in one case. And that one case is going to be the case where this stuff comes in, this horrible, not differentially structured data come in to our operator. And our intent is actually to then feed this to an arrange operator just downstream. So like a not uncommon thing that we'd want to do anyhow is to take this data once we've produced the right data and arrange it by its primary key. Like that's a pretty standard thing we do in Materialize, because you show up with a bunch of data, you say it has a primary key, we're kind of guessing that you are going to be interested in using it by its primary key. Either like joining it by its primary key or doing various other things for which it makes sense to have the data arranged by the primary key. Now, in dataflow terms, this is sort of annoying because the arrange operator is downstream from the operator, right? So the arrangement that we've done, we've put together, let's say, a big pile of data here that is the indexed representation of this collection. And things would make a lot more sense if operator were downstream from that, but of course it can't be downstream from that because it has to feed it in the first place. So what do we do? Well, my plan is, what we're going to do is we're going to take advantage of the fact that this collection has handles to it that you can share around pretty much arbitrarily. And we're going to be a little clever and share this handle back to the operator. This is, I'll be careful drawing this, not using a dataflow edge. So we're going to use just the sharing mechanisms that are present in timely dataflow. So the operator is allowed to have a closure. The closure will capture something that gets to be this arrangement, which means the operator can look at the current state of the arrangement. You might worry that there's some potential for weird deadlocky type things here, and that is absolutely the risk that we are absorbing by writing this. But fortunately, I'm pretty sure that we aren't going to have any problems here. And I can try to morally explain why that is. So this operator is going to get data that have timestamps on them, and it's going to act on that data once it's sure that the timestamps have passed. So like, for example, we might have an interval of time that starts at 0 and goes up to some t. And when that arrives at the operator, all the data associated with 0 up to t, the operator can say, well, in this case, it's pretty easy because 0 is sort of a nothing time. But it can say, what was the prior state? And 0 is a sort of boring starting case, so it says, well, great, so there's nothing there yet in the collection. So let me just go through whatever changes, records I happen to get from 0 to t. For each of the keys, I'm going to get them up to their state at time 0, which is empty, because 0 is when things start. And I'll just play the changes associated. So in this interval here, then for each key, we're going to go and play the key forward in order. So we will play key forward from, in this case, from 0 to just before t. So we're going to take all those updates. We're going to start from 0 and play any updates that we happen to have forward. By play forward, I mean we're going to keep track of the state, which is the current, optional value that we might have associated with the key, and we're going to take the sequence of actions that we've been told to take, and hopefully that will be great. That will allow the operator to produce all the associated updates from 0 up through t, which can then hit the arrange operator, and they'll actually be proper differential plus data minus data statements at this point. So the arrange operator will work great. It'll actually track the state of the collection. And then in just a moment, when we get a new pile of data that goes from t, let's say, to t prime, we'll do exactly the same thing, except now instead of from 0 to t, we're going to go from t to t prime. Everything else is going to be exactly the same, though. And so each time we need to run the operator, because the time has advanced, we know that we can sort of chill out for a little bit and make sure, like if the data aren't yet ready from the arrangement, we can chill out and make sure that we wait for a moment until we get the correct information from the arrange operator, and can then walk through each of the keys, and life should be, I don't want to say great, like we're still doing some work for sure. We're looking around at stuff we didn't have to look at before. But if that arrangement up here already is gonna exist anyhow, because we were gonna write all this stuff down, then great. We're just looking at it before we absorb some of the inputs. So what we're gonna try to write then is essentially this operator and its interface with the surrounding world. In particular, it's we're going to be aware of the fact that it's going to bump into an arrange just downstream, because we need to give it a handle back to that resulting arrangement. My plan is also to put an arrange just upstream in a way that doesn't actually keep an arrangement, but does do the job of batching up the changes. It's an easy way for us to get clearly delineated regions of time and all of the updates that are contained in them. So that's the plan. And it might be that I return to this picture to point at things, but I'm probably going to swing over the computer now and sort of start typing and talking at that. All right, so we're here in the differential dataflow repository. Let's see what we have. We're just on master. Let's check out a branch. I'm not sure what to call this. Geez, I didn't think of a snazzy name beforehand. Let's do just arrangement helper. I have no terrible name, but what we're going to use it, and we're now going to try to put together. I'm just going to try to put together like an example, basically, of using this operator. We don't actually have to distill it down into a reusable operator just yet. I just want to try to get a little bit of a prototype in place. So I'm going to bust open an example. This is the arrange example. Let's save it out as something else. I don't know. Arrange helper. I did this a bunch just because there's a lot of boilerplate that we can avoid rewriting from scratch and having to remember exactly which arguments go where and stuff like that. That being said, I'm going to basically ignore all of the all these arguments. Anyhow, so what's the plan? So the plan. Let me type some comments here. The plan. So the plan is going to be to accept a stream, timely data flow stream, not differential stream, of the following form. So what are we going to do? We're going to have key, option, val, and a time. I suppose we don't have to make those. We can just make these all be a nice triple here, if that makes our lives easier. The intent is that subsequent tuples overwrite the previous values. Our job is to translate this stream into a differential collection, which is itself just a stream whose records have the form doop-a-doop-a-doo, key, comma, val, time, diff. And that's, yeah, great. So the plan is to build, my plan at least, there might be better plans, but to build a sequence of operators. And they're going to look like this. So there's going to be the input that comes in. It's going to go to an arrange operator. I'll explain why in just a moment. That'll go to our new operator that we're going to write, which will then go again to an arrange. The first arrange up there isn't actually going to maintain an arrangement. That is to say, it's going to arrange the data by putting it into batches, but it will immediately just drop the trace that it's maintaining. So actually, all that it's really going to do, it will really just produce batches of updates. So it's just performing this fairly helpful task of taking disorganized input thingies, just these triples, key, option, val, time, and it's going to lump them up by time and make sure that they're indexed by key, and we're getting to see all the data in a particular time interval. We don't have to do the buffering on our own, and like what happens if things come out of order, that sort of stuff. It'll handle all that for us. So it's just gonna make our life a lot easier. All right, so let's roughly start that. Let me get a better name here. We'll leave these things around. I'm not sure we're actually going to need them. So we are going to, actually, I think we're just going to delete most of this. That's sort of silly, but. So we're going to build a new data flow here, and the time type, we don't really care. I think it's going to be probably important that it be totally ordered. Right, so this whole idea we have of the stream of these changes come in, and there's really a sequence of actions that apply to the key, kind of implies that this is probably only going to work for us for totally ordered times, like integers, let's say. It might be worth thinking about what happens more generally, but my guess is that you gotta be a lot more careful if you want to produce multi-dimensional times out here. If you're doing bitemporal work, you might need to be a bit more explicit about what's overriding what other things at what moments. Cool. So you have two overwrites happen at incomparable times, and that's the last thing that happens. What is the final state of that key? It's sort of hard to know ahead of time. All right, so let's move this probe thing inside. We're also going to want an input. And to be honest, I think most of these things have, I think we just do input handle. And I think we can also just do probe handle down here, actually. I might be wrong. We'll find out. These examples aren't necessarily always up to date with respect to all of the idioms. But typically, the input is the sort of thing we're going to use for the beginning of our data flow. So this input up here. And we might imagine having a probe at the end of the data flow, so that when we're testing things, we can actually see, in our outputs, did anything make sense? How do we drive the data flow around so that we don't just do a big batch computation and put all the data in. All right, so the gist is going to be that inputs have this particular form. These are timely data flow streams. So probably the first thing we want to do is to do input, it's going to be scope dot, geez. Say it's input into. I haven't done this actually in a while. Let's check out some other examples. How embarrassing. What is a great, so like Grassband for sure has lots of comments. Do we have inputs here? Yeah, we have lots of inputs. Input handle? No, we don't use the input handle here. I have a lot of sympathy for people who say that the timely differential are hard to figure out. These things surely have input handles. Oh, what? It feels like none of the examples actually use input handles, which is oh, and this is a totally different input handle too, isn't it? What the crud? This is a great way to spend our time. All right, so I guess what we've done a lot of in differential is use new collection as the right idiom. We're not going to want to do that because we actually need a timely data flow stream. So let's wander over and grab new collection and pick it apart. So a new collection produces an input session and a collection. And the implementation of that is roughly this. Yeah. So data to stream. So let's do this. So this is one way to get a new input handle. I'll just do it this way. This isn't really how I prefer to do it. I kind of like creating these handles. Generally speaking, creating handles outside the scope, so that we can then use them down below to drive things around. Delete all this nonsense. But let's try it out this way and try to clean it up in a little bit. We'll get a bunch of compilation complaints and stuff like that. So we have this input handle, which is going to be how the data are returned or sort of managed. We're actually not going to want to use, how's this one annoying? We're not going to want to use a differential input handle because this is going to be a timely input, not a differential input. Let's just try a few things. We'll fix exactly what this call is later on. But I want to say like scope dot input from input. This is going to be our timely stream. Then we're going to do some things to it immediately. For example, we're going to rewrite it to be, so things are coming in, let's say, as key, option, val, and time. We're going to rewrite it to be something else. So we've got key, val, time. Let's make it instead be key, val, time, and I'm just going to say +1 here. So we want to make it look a bit like a collection so that we can use an arrangement. Since we're not actually going to be maintaining the arrangement, it doesn't really matter that we don't retract things or whatnot. This has the potential, I suppose, to allow people to retract before it lands, retract something at the same time. Hopefully no one ever actually uses that or needs to use it. But so transformed, we can totally just turn this into a differential collection. This is really just a statement that says, if your stream has the right types, data, time, diff, then you are welcome to just call it a collection. We're going to arrange it hopefully that's sufficient, but maybe arrange, I think maybe arrange by key is what we want there, to explain that we want to use the key as the key to the arrangement rather than the pair itself. Now, having done that, we're going to want to just pull out the stream from the arrangement. So an arrangement has two things in it, a trace and a stream. And we just want the stream. Particularly, we want to drop the rest of the arrangement. We want to drop the trace so that we don't actually do the work of maintaining this collection, which will grow unboundedly with time if we did try to maintain it. All right. Now, at this point, the data are actually nicely sort of shuffled, but the stream will be a stream of batches. So what we can actually do is write a map operator here. This is going to be our exciting operator. And it's going to take in a batch and do something with that batch. We don't know what that's going to be yet. The intent, though, of course, is to take these sort of k comma v comma t statements to differential updates. And having done that, we're going to arrange again. So let's just talk through this. We could probably try to get this to compile before doing anything particularly interesting. But this will produce an arrangement of the post, say correctly maintained key val pairs reflecting the input sequence of new, update, and delete statements. Let's call it insert, actually, just because now everything has 6 characters. That's just super visually appealing. Great. So this is going to produce that arrangement, which might be useful to us to return or to hand back. This is just a demo, so we'll probably just look at the output and make sure it's correct. But it's also going to provide something sort of useful to stash or to hand back to this map operator, right? Who is going to have a hard time doing its job correctly without access to this arrangement. And you'll see we'll have to do a little bit of a tap dance there to define the map operator first without actually having that particular thing, and then handle back to this arrangement. But first, let's try to get all this crud about like inputs and stuff sorted out. So we do a cargo check, example, save this, range helper. Hopefully this is going to complain violently about, there's no, oh yeah, cool. That was actually right. So we will just throw these down here. I kind of like putting these locally to where they're used so that if I comment out text, I don't have them up at the top of the file, messing up the world. Mutable reference, okay, that's fair enough. Mutable reference. No method arranged by key. So I think that's I had hoped that was this. All right. Right. Oh, good. Sorry. So actually, this stream is a timely stream of batches, which means this is still a timely stream of. To be honest, we don't even know yet because we haven't given the type inference enough to drive things around. But we're going to need to do as collection down here because we're going to produce a timely stream of differential updates. I wonder. So we're going to have an issue with type inference until we actually. I think. Jeez. Hope there's a type inference problem. Otherwise, things are weird. Yeah. Okay. So it can't really figure out what's going on here, which makes some sense. We could say in the input handle what we need here. I forget what an input handle actually has attached to it. If it's time and then diff, or if it's let's do string. The times will be usize. Sorry. So the keys, let's have the keys be strings. Let's have the value type also be string, and the various other types will be who knows what. So I'm just going to try to write this a bit more generic looking at least. Key, option, val, I don't know, yeah, usize. And I forget if let's pull open the timely repo at the same time. I'm just curious whether the I get the order of the generic arguments backwards. So actually, sorry. Okay, it's gonna be what the heck? Some horrible. Is this? This can't be the only. Sorry, yeah, this input handle isn't right. Timestamp and then data. All right. So we're gonna do a usize over here, and our data are going to be these key, option, val, usize triples. So let's save that, and I think we still have some problems because the 69 is probably right. This one down here doesn't really know what's going on. Though we can find the right can we find the right parameters for as collection? I mean, we can always just put some credit at the end that won't actually get executed, like nuisance. Yeah, let's just yeah, well, I guess we'll do a thing here. So like the plan is to produce key val triple, so like key dot to string val 1, 1, let's say. This is not something that we ever actually want to produce. We're just trying to use it at the moment to drive type inference. Yeah, great, it works. Okay, so let's delete all the code that we don't actually need up here. We don't need timely order product for sure. We don't need a scheduler. What's this complicated example? It must have been. Input reduce and join core. Reduce, join core, definitely not. Input, definitely not. Iterate, consolidate, absolutely not. Nice. And there's some unreachable expression because of our unimplemented. We've already, yeah, we don't like blanket imports, so let's ditch that. So we're gonna need map. It looks like input and map. And reachable expression. No one cares about the batch. We're gonna fix that for sure. Why aren't we using our arrangement? We're going to use that for sure. The timer, yeah, to be honest, probably don't care about timers. Probably don't care about index and Pierce either. So these are the when we have multiple workers going on, each worker's index something out of a certain number of peers. We're not going to care. One of the reasons, by the way, that this is, I think, relatively easier than other things we might do is that all of the work that we're about to describe is going to be worker local. So like once the data are shuffled by key, this is all just purely like look at the previous value of the keys. We don't need to do any data exchanges or any complicated stuff like that. So it's a bunch of worker private operations that go on. This basically built great. We could try running it. Hopefully nothing actually happens. I have no idea. We don't produce any inputs. Let's just try running it. Oh yeah, looking good. great. It did nothing. So that's wonderful. We did nothing quite quickly. So good for us. All right, back over here in the program, we have this region of code that's a bit confusing. What are we planning on doing here? And my plan was to have some shared state between this scope and the closure inside, which is going to be a shared, which will have type, I believe, RC ref cell of option of something horrible, which is going to be RC. Could have just typed this out and you would have seen the type, I suppose. It's actually going to be the trace handle is what we're going to put in there, but figuring out the type for that is sort of annoying. So so we're going to want actually a batch down here to more or less share. We'll have 2 copies of it. We're going to have 2 copies of this. One of them is going to be kept by the scope and populated at the end of this, this statement down here, but essentially, which is going to be, I guess, let's say shared 2.borrow mute gets some arrangement dot handle. You have to do that. Well, we'll find out in just a moment. And this folk down here is just going to capture shared 1, so it's going to get a copy of shared 1. So let's do. No, hold on. How do I do this? Sorry. Typically, I leave the unimplemented at the top and write the stuff below it, and then ditch the unimplemented one when I'm happier with it. So this will be something like shared 1 dot. This is some trace things. I don't know. What do traces have on them? I forget. Let's imagine they have a length. Probably don't. Okay, actually, I have to put in ridiculous things like that. All right, so we don't have the RC module in yet. Let's grab that. No method name cell. Oh, okay, cool. We can just print out if it's is none. Probably handle isn't the right thing. Probably trace is the right thing. That whole thing is a trace handle. So now we need to, looking at the errors over here, we need to indicate this is a move. That is that the closer shouldn't borrow a reference to shared 1. It should actually just take ownership of shared 1. That's a legit thing to do. And now we have we've got a program. Doesn't do the right thing yet, but its structure hopefully is more clear to you. Yeah. So okay. So this is now the rough structure of the program, and I think from this point on, just about all the work is going to be in here. So inside this map operator, where we need to start using this shared trace in a productive and informative sort of way. So so get ready for that. Okay. What happens for each batch that we receive? We are going to receive batches, and hopefully, let's imagine we receive them in order. So this could all be lies, but like each received batch assumed in order, and we don't really need that assumption, but we're just gonna structure the code that way to begin with. So we need to queue this up essentially, until such a point as the shared trace's upper bound has actually hit the lower bound of the batch. Which means that we have all of the updates in the shared batch, the shared trace, up to and just before the moment that the batch starts. And this is going to be crucial for us actually getting a correct reading out of or correctly updating and producing all the appropriate changes associated with this batch. So that means we're going to need to do two things. We're going to need to continually, like each time we get a batch, we're going to need to probably stash it in some list, some little FIFO-y type queue. Let's imagine we'll have a queue dot push back the batch. So no matter what happens, we're going to push some data into there. And then we might do a whole bunch of work, actually. So now that I think about it, this might want to be flat map. Which is to say, for individual things that show up, things like batches, we might want to produce multiple output records. Not just because a batch might hold multiple records, I guess that's the most obvious reason, but also because when we get a batch, we by looking at the trace, may or may not be able to do anything just yet. So that's potential concern. So so let's think about that. So this will probably progressively get more and more complicated the more I realize that I actually need more stuff too. But let's just start writing the initial structure of it, and we'll see where we go. So we're going to enqueue the batch because shared one might not yet be ready to process. And there might be a lot of other batches ready to be processed, and we're going to do them presumably in order. Great. So now let's figure out. We're going to need to figure out how to capture the upper bound of shared one, and there's some methods on traces to do that. I just don't want to context switch quite yet. So we're going to let upper be something that we haven't quite implemented yet. And we're going to go through the queue, and as long as the lower bound of batch equals the shared upper, so we're going to advance shared upper as we go. Also, in case we get a bunch of batches that we can chain together in sequence, we will. Should we do that? Oh, this is exciting actually. Sorry, it's exciting because there's a clever way to do this and a less clever way. So if we have multiple batches queued up, for example, we totally have the ability, if all these batches line up, to grind through all of them. But we have to be a little careful because not all the updates will actually have made it to the trace yet. So if we're processing 5 batches in a row, we can, for each key, get to the correct next state at the end of each of the batches and just continue on to the next one. But if we just restrict our attention to the trace, we won't actually find all the right updates there. So we want to be a little bit careful here. Maybe we'll just do a batch, and that will be sufficient. I don't know. It'll give us some structure for the moment, and we can think about being a bit more clever. There are absolutely clever ways to take multiple batches, stitch them together into one larger batch that we can iterate through. And maybe we just want to do that actually. We'll see as we try to actually write some of these unimplemented bits of code. All right. So what's going to happen is if the shared upper is equal to the lower bound of the first batch, we should be able to grind through, pretty much doing us all of the batches, right? If we're going to do our clever thing here, as long as the batches have sort of come in order and without any gaps between them, that's exactly what the arrange operator does. So should be the case. So let's see. If we look at the queue and look at its first element, so like peak front, I have no idea what queues support. Then if it's the case that the first dot lower is equal to the shared upper, we'll do a bunch of stuff, and in particular we're going to drain a whole bunch of stuff from the queue. Great. Though we're probably going to need to be a little careful because this will borrow the front of the queue, and it's going to make it hard for us to drain it anywhere down in this context down there. So let's so drain queue is actually going to be equal to this option of a batch there. We're going to map it to be map, meaning like if it actually is something, then it's a batch. So like b dot lower equals shared upper unwrap, and it really doesn't matter if the queue is empty because draining it is so unwrap or false. If there isn't actually anything in the queue, who cares, right? We can either do the draining logic or not because there's nothing to find. Sweet. So this is going to determine if we're able to go and drain our queue. And if so, and the reason we break this up this way is because we don't actually want to sit on a reference to the queue, so which will prevent mutating the queue. But if it's time to drain the queue, then we're going to for batch for each batch in the queue when we drain it, we're going to do some logic. And exactly what we do here is not entirely clear, but I bet what we can do is put together a big cursor that represents a whole bunch of these batches all at once, and then we can access that cursor to walk through the keys. So a cursor is a way to take a bunch of these batches and to navigate them by key and by value and by time, and that's what we want. Unfortunately, we can, I believe, make one of these out of a bunch of batches. And then, so like up here, let, actually, to be honest, I think we're just going to need to, just dash all this stuff in a vector. I believe that's what, so to be honest, we probably didn't need a queue at all, did we? We probably just needed a vector. Let's put these in. Oh well. And what we're going to do roughly now is create a cursor using this list. Let's look around in the differential thing to see if we can remember how to create cursors to things from batches. So a cursor list is definitely the thing that we want. But let's take a look at all of our. This is just a test, isn't it? Oh. So a cursor list is something that takes a bunch of already existing cursors and already existing storage. In a sense, storage is the batch, it's the big pile of data, and the cursors are the offsets into it that allow us to sort of navigate around without mutating the underlying storage. So the actual way to build one of these cursor lists, I suppose, is to take each of the batches and from each of them get a cursor. So if we will do something like this type of thing, and actually I guess we'll be able to rewrite the so for batch in queue.train. We'll get back this exciting structure here. And all that we're doing here is just getting both a cursor and a the storage, which is again is just a reference to underlying data. I have to give it a different name, don't I? Yeah, great. I'm sure there's an idiomatic way to do that. I just don't remember what it is. Great, and we are now going to try to create a cursor list. So like let mute then in principle what we have now is a cursor that's able to walk around by key through our collection of batches, and will tell us about things in those batches, keys that we find in those batches, and also diffs that have gone on in those batches. And all that this is really doing again is putting together these key val time dribbles for us so that we can go and look at them. So this is I'm going to say this is our input cursor, because we're actually going to have a few different cursors here. We're going to have also a trace cursor, which we'll need to get from our shared one down here. And we'll have to look at this, but I think actually we're going to end up getting a trace cursor and trace storage from our shared one dot. Let's see, we might need to actually borrow it. Borrow. I'm not sure if we need a mute or not. We'll see. So what's going on here is that the shared one is actually a RC, so ref counted ref cell. A ref cell is something that pretends to be the thing underneath it, or like gives you access to it. But to get access, you actually have to go and explicitly ask. And when you explicitly ask, it gives you back, essentially it's like a lock or something like that, something that acts as proof that you have unique access to this thing. But that does mean that you need to keep it around, you need to like bind it in the scope, so that when we call methods on it, it does not immediately evaporate as part of the method call. So this sort of acts as a little bit of a proof that whatever it is we're using for this cursor through call, we expect it to stick around for a little while. It's okay to return references to it, so these trace storage things will have references back to this trace. And now the intent is that we should be able to jointly navigate, well, really to be driven by input cursor. So let's look at some idiomatic uses of cursors here. I believe it's basically while key, I hope. Let's see. And each of these things are going to take great. I can give these better names now. Yeah, the storage here, great, good. Sorry, just mentally refreshing myself. So this actually takes ownership of the cursors, but does not take ownership of the storage. And then the storage needs to be resupplied when we take various actions, because we don't actually want the storage to be captured by this particular cursor. One of the intents here is you should be able to write these cursors down somewhere, or like keep them around and return to them later without actually holding a lock on the underlying storage. You have to, you do have to keep it around, but you can use other mechanisms to clarify that you're not mutating its state. So while we have some key in our input cursor, what do we need to do? So we're almost certainly going to need to essentially just write down all of the val and time pairs associated with this key. The data are grouped by value first and then by time. We want to pivot that around, make it be by time first and then by value. So that's the thing we'll need to do. So we're going to let val times be vec new. We are going to walk through each of the keys. I don't think there's an iterator, so I think we need to again do step through all the values. Both the step key and step value things also need access to the storage. The stepping isn't super exciting, but there's other seeking and stuff like that that you can do, and that definitely needs access to the storage to look at what you're seeing. I think we might need the storage to see if you're like at the end of. So if we try to step past the end of the values in a key, we need to do the right thing there and observe that the key is bumped and stuff like that. Great. So for each value, though, we can do input cursor dot. It's called map times, which it just the times and diffs aren't really maintained in a particular order. So all you really get to do is map through them very quickly instead of navigate through them. They're not in order the same way that keys and values are. And all we're going to do here, I believe, is do val times dot push time dot clone val dot clone. That looks good to me, right? I mean, sorry, you might have no particular opinion about this, but we're capturing these values, and in principle now, if we do val times dot sort, make this mutable, of course, we're now in a position where for this key, we have sorted by time the various things that need to happen to this particular key, which we can then, like as they happen, we can then take some exciting action and ship them. So let's just sketch out what that probably needs to look like. So hopefully we have from our input trace an initial value, or let's call it like a current val, which I'm just going to make equal to none at the moment. Well, I'm going to make equal to unimplemented. Make sure I don't screw this up later. But it's going to be option of val. And now for time, comma, val in val times. I'm not sure why I called it val. I thought I was going to write them down as value and then as times, but obviously that's wrong. What are we going to do here? We're going to, based on our three different cases now, so essentially I think we're roughly going to do a match on current val and val, where there are a few different cases. So we might have, we just write them all out, I guess, some so in some cases there'll be two. We have to do a thing. In some cases, there's going to be a previous value and then nothing. We're going to need to do a thing. sometimes there's going to be nothing and a next value, and we're going to need to do a thing. So the typing is exciting. If you're familiar with my setup, I have interesting programmable keyboards that haven't properly trained me yet how to use them. And so there's lots of exciting typing misadventures that slow things down. So we kind of think this last case shouldn't really happen, though. Probably we should write it out anyhow to make sure that we're not, if we wanted to print an error, we could. This is the case where there is no current value and we get told uninstall it. Now, clearly, that doesn't make a lot of sense, so we're not going to worry too much about that. So in these cases, we're actually ready to go with some stuff. I'm going to write session. Session's a thing we haven't defined yet, but this is the output for the. We're in a flat map, so I actually don't need to write this yet. It does mean I think we're going to need to make this not be a flat map just to make things more complicated, but that's too bad. But what we can do for the moment is just we're going to produce two results here. So we need to produce something that looks like an iterator. The moment in Rust, that means we need to put together a vector if we want to produce two things, because it's just a pain otherwise. And what we're going to produce is two records. So key.clone, comma prev. Prev is owned because it's an option of val. Time.clone, -1. And also, sort of frame these slightly differently here. Also key.clone of next, probably .clone because I think it's oh no, we cloned it up here. Okay, sorry. We didn't actually have to clone it up here. Maybe we shouldn't have. These all have lifetimes that refer to the input storage stuff. Well, anyhow, so since it's cloned, let's just not do it here. Clone. You don't say +1 in Rust. It's bad, even though I'd love to, but you don't. Great. In the case that we just needed to uninstall a previous value, we just produce this statement. It needs to be an iterator though, so we're probably gonna make it a vector because it needs to be the same type of iterator. But there we go. So we'll just put that in our result. Great. Actually, this logic is, hopefully you notice this logic is going to factorize brilliantly. So now what's actually going on here is if we had a previous value, no matter what happens, if we had a previous value, we should delete it. And no matter what happens if we have a new value, we should emit it. So this is probably a lot simpler. I think this is just if let some prev was current val, then we are going to need to send so we're creating a big vector of stuff to write down here. Output dot push, and we're going to push always if there was some previous value, a retraction, and if let next equals val, then we're going to push a positive of this next thing. And in every case, current val is going to become val. So there'll need to be a clone that goes on there. But all right, and this is not the right way to write this operator, but actually what we can do is build up this output list for everything, and I mean, what we actually want to be doing is sending this stuff as soon as we know what's going on. But let this be our output queue. And everything else is nonsense. And like in principle, this is not correct at all. But like in principle, this is roughly the sort of thing we want to do, which is grab, make sure that we, we haven't even, sorry, we still have some unimplemented code here. Yeah, great. Actually, let's write that now before we get too far along here. So what this is going to look like is this is going to start as none, just because maybe there's nothing. We are going to seek in the trace cursor. So trace cursor dot seek key, and we want to use key. This key up here that's from our input cursor. It might be there, it might not be, but we're going to seek it anyhow. And what we can do now is the key here, there's cursor is at some key now. It might not be the right key for us. So if it's the case that trace cursor dot just some key. I think key is a reference, so we can just copy it. So if it's the case that we're at the exactly the same key, we need to go and figure out exactly what the value is here now, and there's a few ways to do this. What we can do, so basically we have access to the full history of the trace. It's not necessarily just a single entry in there though, so we have a bunch of values. Ideally, unless there's a bug, all but one of these values accumulate up to 0. If we add up all of their changes to up to the current time, which is defined as shared upper, then we should only see one value set to true. We could bail out the first time we see this, or we could run through everything and complain if we ever tried to set current val to something that isn't none initially. So let's try that. So we want to do again, while let some val gets trace cursor dot val of trace storage, something that ends with trace cursor dot step val. We are going to want to do a map times here that doesn't need to do anything complicated like accumulate stuff. It doesn't need to like build up into a vector or something like that. We just need to accumulate up these differences. So if we let count be 0, and we do trace cursor dot map times. Times and diffs all over the place, and what we want to do, actually we kind of know that the trace cursor only contains diffs less than shared mumble anyhow, because we haven't produced those outputs yet, so we should just add everything up. So we can even just ignore the time, I think, and just do count plus equals diff, at which point hopefully we have, so we're going to assert that count should be greater than 0, right? Otherwise something really messed up's gone on. Like, since we're producing the output for this output of this operator, which is the input of the trace, we should be able to control this and make sure we don't screw that up. Sorry, I apologize. Greater or equal to 0. And we're also going to want to let's see, if the count is greater than 0, we're going to want to assign current val. But we should assert that, and again, we're looking at a trace that we've produced. This is the shared trace, so like it's within our power to keep this correct. So hopefully this isn't an assert that's firing a lot. So if the count is bigger than 1, and to be honest, it probably should be exactly 1. It shouldn't be. Yeah. So let's assert the count is either 0 or 1. If count is exactly 1, then let's assert that the current value is none, and let's set the current value. So this should yell at us if we ever have anything other than a 0 or 1 count. This is meant to be this primary key that holds only one record. So like, you don't get to increase its multiplicity, and there should only be one. So the same value can't occur 5 times, nor should there be 2 or more different values associated with it. And I hope this logic does that. I'm not entirely sure, but yeah. All right. So we determine the initial value associated with the key. That's great. Up here, we're going to order sequence of updates by time. I guess then by value, but like hopefully we're not. I mean, if we have to break ties, if some horrible person has written 2 overwrites at the same logical time, I suppose we could resolve them however we want. We should probably do deterministically. So that's good there. Right. So this is now a thing. Again, it's still not correct for reasons that I will try to explain, and possibly we'll actually get around to fixing. Though I might also just punt it off for a little bit. It starts to get a little bit more in the weeds, but let's see how this looks. Just cargo check. Oh, sorry. I have to actually check an example. Great. So yeah, this is terrible. This is just not correct. Rust at 86. I'll have to check to make sure this is exactly the correct thing to do. I think cursor probably works as well. When you have something that supports cursors, you can either ask for a cursor through everything, or a cursor through a particular boundary in the frontier space. So to be honest, I think this could probably just be that. Again, because we've already sort of verified that we have all of our data ready to go. And one thing we didn't do down at the end that we should make sure to do: update the shared upper frontier. Suppose what we can do is, for each of these batches that we process in order, if we don't need shared upper anymore, no, we don't, then as we process the batch, we could just set what is shared upper, actually? I have no idea what we've decided it will be. Oh, we don't even know yet. Okay, cool. So let's just make it batch dot upper dot clone. We'll find out what type it is. I think it's an anti Sure, jeez. We'll have to see what it is. Let's fight some other things here. And all right, cursor list is something that lives in differential, and we'll need to. Don't remember where exactly it lives. So it's going to be in trace cursor list, apparently. Let's see if that helps us. Q. Yeah, we're gonna need. Okay, so we need to define a Q to create this closure. One cutesy sort of way to do that is just put a scope for each of our places that we define a closure. I'm going to do like let mute Q. Actually, we said this wanted to just be a vector. It didn't really matter. I guess since we're draining the whole thing every time, just make it be a vec. Now, this is the result of this scope is the closure that captures a few things, and in particular is going to need to capture more than, sorry, I just want to close this down so I can do. This closure ends where here, and so we'll need a So queues now just have there's just a vec. We are going to drain things that way in Rust. Let's see if this works. Sorry, not works, but like no field lower on ref cell of blah 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 word val batch. That's right. There's definitely no field lower. There should be a method, I think. No method named cursor on word-val batch. Okay, we need to bring in a handy little trait here. Not sure where this. Let's put this trait up right here because it might also be what defines the lower method. So expected some cursory thing. Let's have to check out exactly what cursor returns. Just upper, yeah, no, it's upper is a method, not a field. No method cursor. Okay, well, we'll have to look into. No method named key. Oh, okay, we just need the trait again. That's good. I'm just sort of cleaning up some of these errors that are obvious, not obviously like are noisy, and we can reduce them. All right. Map times does take two parameters. It takes storage and the closure, so we need to also supply. I think it takes the storage first, just because it'd be really gross to have to put it at the end. Let's go figure out why cursor doesn't exist. So if we look for the not tests, the cursor methods associated with, for example, batch reader, gives us back a cursor, and we're supposed to know what the type of the storage is. That makes a lot of sense. All right. So each of our calls to cursor really should just be this. And trace storage is going to be a bit more complicated, but I think it's just going to be a. Let's try writing it down. Might not actually need this because it might deref to the right thing, but I'm not entirely sure. So input cursor is still, yeah, just one of these things, but in input storage, I think it's actually legit, maybe? Where was this complaint here? All right, so, oh, bother. So I think we get a cursor here from batch cursor, and we push the batch in as storage into the input storage. So I want to update the shared upper before I have to get rid of I have to release control of the batch. But the batch itself is the thing that counts as storage there. Unreachable statement. Yeah, that makes sense because we still have the unimplemented. No method named cursor found for ref blah blah option. Okay, this is because we haven't bothered to confirm that we actually have a trace. That's a good call. I'm going to be a bit sloppy and imagine that we are guarding this properly. Or let's see. Yeah, to be honest, really, this cursor can just be an option type thing. So if this is none, we shouldn't be doing anything. Sorry, we should be doing all of the work here, but we shouldn't worry about the fact that we can't look around inside this. Let's not do it. Let's do that, and we'll wrap all of this with a don't do anything if we don't have our trace yet. So obviously we can look at the code and see that this isn't going to run until the trace actually gets set, but we only know that because we happen to know that timely and differential data flow don't actually run an operator until the control is released. So like this could, at the moment that this flat map call gets called with this closure, it could start running in principle, but we happen to know that won't be the case. So we're just going to casually unwrap and say, like, I don't care. Like if we started running, we know that that's legit. All right. Type annotation is needed for this horrible thing. That's fair. That probably just means we've screwed up the type somewhere else. Let's check out what cursor wants. So when I call key, I think key might actually might be the wrong thing. So when we call key, we actually get a ref. So get key is the way to get an option as opposed to just forcibly getting a ref. This will panic. In some cases it doesn't tell us whether we found the right thing. So I think we want in each of these cases a get, and here a get of the val, and there must be some other places we did that. Yes. Get. All right, we're down to relatively fewer errors here, but we have to figure out some type T. So I was kind of hoping that this would actually tell us exactly what the type is here because the arrangement, okay, but probably the fact that we have some little cycles here, that this arrangement's only determined by the actual production of this sort of thing over here, just screws this up entirely. So let's see if we can figure out what arrangement.trace will actually be. If we do an arrange by key, this is a method, it returns an arranged of a blah 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 blah, and just we'll check the .trace field if that's what we're interested in. So we want to check out an arranged and see if you have one of these types. To be honest, it's probably going to be this type. If we have one of these types and our arranged struct, what is the trace? So let's go look for this. The trace type is indeed this argument. So I believe that although there's a bunch of horrible So I have to go look up. Val, this should be I think this is just going to be a usize. Let's see what happens if we do that. Default val trace is almost certainly, and trace agent are almost certainly not in scope, but we can find them. Yeah, each of those are great. Let's just steal that. And default val trace is found where? I see. Word val spine. Use. Who? Yeah. Okay, I got some more fully qualified names here. That makes sense. Method cursor found for this, so we need trace reader. We don't have trace reader in scope. Oh, I thought we had this in scope. Oh, not yeah. I see. We had batch reader, not trace reader. They're different. Okay. Fascinating. Okay, we got some really wordy. I bet. If we look over in, over in trace and we say, what is its method cursor? So these two things, batch reader and trace reader, are different. And cursor here is going to provide, we can't really read this, but for the trace case, it's actually give us back the storage. So trace reader gives us back the storage, batch reader, the batch is expected to be the storage. So that means that when we got our cursor for our trace, we should actually have done that. Now, trace storage isn't nearly as weird. All right. So we just struck vec, found string. What? Expected, so we showed it a string. I think that makes a lot of sense, to be honest, that we showed it a string. But it's like, hey, why didn't you show me a vector of batches? Okay, well, we clearly screwed something up here. Compare, okay, well, let's fix this one down here, because this one is, can't compare a string with an option of string. All right, so that's just because this should be get key. And something is screwed up in all of the type inferences, such where we've accidentally compared a batch with a vec of batches. Actually, somehow, what have we done? I mean, the place where we have vecs of batches is input storage, but in what world are we? Well, we can try to. It looks like trace cursor is. We don't just have like the types backward on this, do we? Maybe. Let's look at the cursors and see. Make sure that we have called things in the right order. Cursor. So things like get key. Take the self and then the storage. Seek key. Takes the storage then the key. Okay. So storage is always first. So that just means that when we did seek key here, we should have done things in that order. Hey, and it compiles. We've actually done that already. We've updated the shared upper. Let's tidy this up a bit. We don't care about the diff. Is that true? That's a different place. Sorry. Yeah, right. So in our very first input batch stuff that comes along, we don't really care what this is implied +1, right? Up here. No, sorry, up here. We had to put a +1 onto it. This +1, and we don't really care what that is when we read things back out. So that feels, we want to verify each of these unused statements, just because, often they're representative of bugs. Value assigned to shared upper is never read. That's probably just because we have an unimplemented up here that we don't use properly. I'm guessing that shared upper should be vec of, I'm going to say 0. This is initially it's a vector containing times that describe the frontier, and the very first thing it can be, since its use size is 0. We're actually gonna, so there's still a whole bunch of bugs in here that more or less boil down to we can't really use flat map, unfortunately. Or maybe we could, but it wouldn't. We could make it more correct and less performant, I suppose, or less live. But we should. There's some stuff we should do. I'm just gonna leave some comments in them first. So just because we received a batch doesn't mean that the batches before it have actually been processed in the arrangement on the other end of us. They may well have, because just of the way that differential and timely work, but we can't really rely on that. So we do need to make sure that shared upper tracks this upper bound, and it's a little bit more complicated, unfortunately, than just setting it to the upper bound of the last batch that we've received. Because although we have shipped that batch outwards, it's some statement here is wrong, right? Yeah, this is wrong. Although we have shipped that data, that doesn't mean that it's actually present in the arrangement yet. So fortunately, there's a method on traces that I think tells us the upper bound of a thing. Trace reader, which gives us a few things, but read upper is one of the things that we can do. So I suppose actually we could just that's not the right way to call it. Read upper, which requires mutable borrow of self for some crazy reason. I think some of these traces have to mutate internal state. Let me do this. So we need an anti-chain, and then we call read upper on a mutable reference to it. And this populates shared upper with the right stuff. So this, I suppose, is just a way of avoiding an allocation or type, dancing around some type constraints. This is in sorry. So we borrowed it. We want borrowed it mutably. We want as mute.unwrap. So we need to assert that it's not a none, basically. All right. So now we have some fun little test we have to do here. Shared upper is an anti-chain, not a vec. I think this will do the right thing. Elements is a thing that. Okay. Okay. This might be easier than I thought. It needs to be immutable. idea how many of these things can assign twice. Oh, we're in. There's a lot of code analysis that didn't happen because of that unimplemented thing. So we didn't check all of the code down here basically for like lifetimes and cool. That's makes a lot of sense actually. We definitely do not need the shared upper anymore because we're just rebuilding it each time. I suppose we could do, but to be good people, we could build this once and not redo the allocation, just repopulate it each time. And something terrible is going on over here with can't borrow data in a reference as mutable. Where's what's going on? Does the cursor method require a mutable borrow to a thing? Let's find out. Cursor does require mutable borrow of self for reasons that, unfortunately, almost certainly are legitimate, but are hard to justify right now. Trace. Oh, okay. Do need to borrow this as a mutable thing. Cool. All right. So this checks. It has this one major bug in it that I think is going to require us to not use this flat map operator and sort of bundle it up as a separate operator. And that bug, unfortunately, is that this only gets called when data arrive, when like a batch comes in or something like that. And when the batch comes in, the arrangement downstream might not be ready for it. And we've thought of that. We put it into this queue and say, great, let's run when the batch actually, when some data actually arrives. But something might sit in this queue for quite a long time, actually. So if we push a batch into here and we say like, we're not quite ready to process it yet, put it in the queue and then don't send any more data for a very long time. This code won't run again. It'll just sort of sit in the batch, even though we might have gotten to the point where we could process it now. The very next bit of data that gets pushed in should prompt all of the processing. Like that should be good to go at that point. But if there's ever a little hiccup, then folks will just sort of sit there in this queue and nothing particularly happening. I don't think it's not immediately obvious to me why it would be wrong if it's wrong. Incorrect answers. It's not correct in the sense of it's certainly not full credit performance-wise, but yeah, I'm tempted. Well, let's see. We could try running it and seeing what happens, and that's interesting. But what I'm tempted to do, maybe do that, and then either case, whether it works or not, to take a pause for this particular recording and come back to it. Either come back to it in more detail in a future recording, just to really get into the weeds of what do we need to do to make this thing react properly, or do that just sort of quietly off screen and just push the working code eventually. So let's see what happens if we've built a data flow here that does some stuff. We could now repeatedly put stuff into that input and step the worker, and so this is how we would drive this around. So let's just for the moment try that out a few different times. So let's do something like input dot. What are these? Send, I think. Input handles have a new register, flush, close, epoch, send batch. Is there just a send? Send, great. So we can just send some data if we want. That's great. Let's just use integers. Oh no, we called it strings, didn't we? Crud. All right, so I guess we'll do a bunch of things like. So we're gonna send a key, a value, and some time. Great, that's a thing we could send. We could also, value. We might change it to be some other famous Franks. Sorry. Great. We might in between these things. I'll change the times in just a moment. Might make this be a none. So if we do that, we also need to call the advance to. Let's just pair those up. So advance to 5, advance to 9. And this last one's going to be probably a bit of a problem because if we don't have any more data after it, it's not going to really do a great job of prompting transmission. And after each of these, let's do a worker dot step. Or we don't have a probe yet. We could put a probe in. So we'll put this back in. And before wandering away, we will, I guess it's sort of just right down here, isn't it? How does probe, I think it's probe width or something like that. Let's try it. Call that something other than probe handle? Wait, what the hell am I looking at? I just called it probe. Okay. Super2. So this lets us do things like so let's make sure that we actually push that message all the way through the system. That may not actually be correct, as we've discussed. Like, the flat map may not fire the right number of times because we don't actually need this. The worker will finish running by the when the closure ends. No method probe. Okay, we're gonna need another trait brought in. Okay, let's get catch on fire. Everyone ready? I'm not actually sure what. Yeah, good. Okay, so panicked. It's hilarious. I mean, hilarious. It's totally legitimate. Let's throw an inspect in here so that we can see what's actually going past. Do I have to remember where to find various? Why is it so problematic? Okay, over here. So this will show us at least what's gone past, and maybe we can learn. Well, like here's some obvious screw ups. That if you just noticed, this is a -1, it should have been a +1, obviously. No method inspect. Come on, input. Sweet. All right, so it did a thing. Let's see if this corresponds to anything correct. But like the fact that this worked, if it did work, is purely dumb luck. just because we haven't been paying enough attention to asynchronous issues about whether the arrangement's ready or not, and that it worked single-threaded on one single input is not evidence of that. But what do? We sent with key frank some data at time 3. That's great, it actually showed up. At time 4 we wanted to change it, and indeed that happens at time 4. We retract the previous value and produce a new value. At time 5 we wanted to just delete the key, and at time 5 we do in fact just retract the previous value. At time 9 we're now inserting something that doesn't previously exist, and so good for us, we do that, and it looks like we also totally discard the data at time 15, and indeed that's exactly what happened. Great. Well, that was to be honest, that was unexpected, but it's good to have demonstrated the intent, at least, of what's supposed to be going on here. I don't think this particular implementation is actually sufficiently hardened yet. There's at least 2 classes of things to fix. One of them is that if the arrangement isn't actually ready to process, then we should make sure to check back pretty soon, essentially. We kind of want to be activating ourselves. If we get a batch for a thing, well, we're pretty sure that the arrangement should be ready to process this pretty soon, right? Because we know that anything that's not in our queue has actually been sent along to the arrangement, so it's like ready to actually put that stuff together. So we could just reactivate ourselves repeatedly if this test fails. If we have something in the queue and yet we are not yet ready to activate, we should yield control and reactivate ourselves. Another thing that we're going to need to do is that trace that we're holding on to, this shared one here, has a bunch of capabilities and historical ability to read historical data that we don't really care about. So it's like by the time we're off at time 9, we really don't care about all of these exciting different values that this collection has gone through. They should all just be collapsed down. That's totally fine. We're not currently giving up those capabilities to look at the historical data. So until we do, there's a bit of a problem. I think we could probably just fix that right now, actually, by saying, roughly what we need to do is all this nonsense again. Advance through, maybe. We'll have to look and see, but. And so there are these 2 capabilities, and I can find what they are pretty quickly. If we go into the count operator, then we advance by and distinguish since are the 2 things. Great. And both of these say, like, what, I don't need, all of my questions are going to be times from this point going forward, and that's totally true. Like we're not going to use any historical distinctions that are not greater than shared upper. So that's handy. Let's see if that still type checks, actually. Yeah, cool. So this is good. This will actually let the trace be compacted as the execution moves along. That means we don't run out of memory and stuff like that. And this operator is actually pretty harmless in the sense that it doesn't need any big historical detail lying around, so it pretty aggressively allows the compaction to happen. Other people might hold back the compaction, but really it's not a big deal. But yeah, so I think I'm going to stop. I'm going to stop there. I'll need to do a bit of a check-in to see like what are the actual defects with the this timing between the arrangement and its data being available and this operator running. But hopefully this is a legit sketch of how you might put together an operator that takes in these weird statements of the form, here's a key and here's the value I want you to make true. Please uninstall any previous values if they exist, with the option to provide no values, which just uninstall some data. And the only working footprint of this should just be this arrangement that we're tracking at the very end here, which hopefully is useful not only to this flat map in here, but also to people elsewhere in the system who think that having, I guess, a collection indexed by first name is a ridiculous primary key, of course, but yeah, the data indexed by some primary key. And cool. So with that, we'll stop. I appreciate any time that y'all have taken watching this, and stay safe and healthy, and yeah, enjoy the time ahead.